Welcome to this session of linear programming part B. Let me introduce myself. I am Ashish Agrawal. I am lecturer in School of Engineering and Technology, and today I am going to cover the course system method, the code of which is ET301A/534B, and I am covering block 2 of unit 6, the linear programming using simplex method. After this session, you will be able to formulate the management problem as a linear programming problem. You will be able to identify the different characteristics of linear programming problem, make an analysis of the problem, solve the problem by simplex method, identify various types of solution, and explain various application of LP in the business and engineering and industries. Now, what is LP? Linear programming solving approach is developed to help managers in making decisions. For example, a manufacturer who wants to develop a production schedule and inventory policy to minimize the total production cost and the total inventory cost. Similarly, a financial analyst wishes to maximize the return on his investment. A marketing manager desires to determine how best to allocate a fixed advertising budget among alternative advertising media. For example, there are different medias like paper, print media, or multimedia. So, in which how he will allocate the resources or financial resources so that he may get the maximum output. Similarly, a logistic manager who is in charge of many warehouses, and he has to allocate the resources from warehouses to the customer. So, this LPP problem will help him to decide that how much he should ship to from each warehouse to each customer so as to transportation cost get minimized. Now, what is the LP problem? It is an optimization problem which is used for maximization or minimization of a linear function of decision variable. Now, here we select the decision variable in such a way that satisfy a set of constraints. The function which is to be maximized or minimized is termed as objective function. Similarly, the restrictions which are in the form of equation or inequations are termed as constraint. Here we are dealing with the equations or function or constraint which are linear in the nature. I am giving you the example that what is the linearity means. I am just giving one example, that is 5x1 plus 3x2 plus 105x3. This is a linear function of x1, x2 and x3. But 5x1 plus 3x1 x2 plus 105x3 square is not a linear function. Now, how you will define a linear program scientifically? It is an optimization technique. I am just briefing all the things which I have already explained so that any newcomer who wants to join or wishes to join this session, he will not feel any difficulty in understanding the simplex problem. Now, the definition of LP problem. LP is a technique based on mathematical theory for satisfying the ways to use the limited resources or constraint of a system to obtain such as high profit, least cost, least time when these resources have their alternative uses. Now, what are the different characteristics of a linear programming or LP? Provide the best course of action which managers should take under the given condition. Converts physical system into a mathematical model. Analyze effect of change in some parameters. Carries sensitivity analysis regarding variation of system parameters as the optimal solution. Then we can extend the linear programming into some advanced technique, for example, goal programming for multi-objective problems. Similarly, for probabilistic model where chance constant, suppose we have 3 vendors and we have their quotas, or we are getting in our warehouse that certain materials have been received by the warehouse. Each time we are getting certain portion of our material defective. So, if in warehouse we are finding certain material defective, we can find out that who is the vendor responsible for supplying this defective item. Now, we will explain the different terms which are frequently used in the linear programming problems. First is the decision variable. In the LPP problem, the decision variable means the variable whose quantitative values are required to be found. so as to minimize or maximize the objective function. Now what is objective function? Objective function is what decision maker want to do. Suppose a decision maker want to minimize the cost, then the minimization of cost is an objective function. Suppose he wants to maximize his profit, so the profit maximization will be the objective function. Now the constant. The constants are the restrictions which are expressed in the form of an equation or inequality. For example, in terms of less than or equal to or greater than or equal to are termed as constant. Similarly, then we come to the feasible solution. After solving the LPP problem, we will find that there are many solutions. So these are the feasible solutions which are obtained through linear programming. But out of this, there will be only one solution which will be optimal, which will satisfy our objective function to maximize the profit or minimize the cost. Now in case of maximization, the objective function needs to be maximized. In case of minimization problem, we have to minimize the objective function. Now there are two types of basic feasible solutions. One is called the non-degenerate. A non-degenerate basic solution is the basic feasible solution which has exactly n positive decision variables. Here none of the basic variables is 0. Similarly, the solution becomes degenerate if any one of the basic variables becomes 0. Now this is a general formulation for LPP problem. Here Z is the objective function, Z is the summation of CZ XZ. This is the objective function, CZ is the different contribution made by the XA variable. Similarly, this is the constant summation J is equal to 1 to n Aij into Xj. This is a constant, and third one is the constant for non-negativity, that is Xj is greater than or equal to 0. Now we will take a simple maximization problem and we will try to formulate into a mathematical model. ABC is a firm that produces a variety of chemical based products. In a particular production process, 3 raw materials are used to produce 2 products, a fuel additive and a solvent base. The solvent base is sold to a variety of chemical firms and is used both in home and in industrial chemical products. The 3 raw materials are blended as given in the table. That material 1, 2 and 3, here is fuel additive and the solvent base. These are the product which the manufacturing unit is making. Now fuel additive has 2 components. 1 ton of fuel additive is comprised of 0.4 ton of material 1 and 0.6 ton of material 3. Similarly, solvent base required 0.5 ton of material 1, 0.2 ton of material 2 and 0.3 ton of material 3. But this production is constant by the limited availability of material 1, 2 and 3. Now what is the constant? That the available quantity of material 1 is available only 20 tons, material 2 is available only 5 tons, similarly material 3 is available 21 tons. Now according to the prices of materials, the fuel additive, the manufacturing and selling of fuel additive can contribute a profit of rupees 40 per ton. Similarly, a solvent base can contribute a profit of 30 for every ton produced. Now we will formulate the problem. This problem means we will translate into a mathematical problem. Now what actually ABC wants, or what the management of ABC wants? They want to determine how much quantity of fuel additive and how much quantity of solvent base should be manufactured so that it should maximize the profit. Now the number of tons available for the 3 materials that are required to produce these 2 materials will limit the number of tons of each product. So objective function is to maximize the profit. Now we will define the constant 1. Constant 1 says that the number of tons of material 1 used must be less than or equal to the 20 tons available. Similarly, constant 2 says that the number of tons of material 2 used must be less than or equal to 5 tons available. Similarly, constant 3, the number of tons of material 3 used must be less than or equal to 20 tons available. Now we will say that what are the decision variables. Here the decision variables are the number of tons of fuel additive and the number of tons of solvent base. Now we will nomenclature it that F is the number of tons for fuel additive and S is the number of tons of solvent base, and these are the decision variable which we need to be found out. Now we will write the objective function. Since the total profit contribution is 40F plus 30S and this is to be maximized, so our objective function will be maximization of 40F plus 30S. Now this is the constant 1. Constant 1 says that the total number of tons used should be less than or equal to tons of material available. Now remember that every ton of fuel additive needs 0.4 tons of material 1, while solvent base, every ton of solvent base need 0.5 ton of material 1. So therefore, for producing F ton of fuel additive and S ton of solvent base, we need 0.4 F plus 0.5 S. So this will be our constant number 1, that 0.4 F plus 0.5 S should be less than or equal to 20. If we go look to the constant 2, here the tons of material used is less than or equal to tons of material available. This is 2 tons, so 0.2 S is less than or equal to 5 tons. Similarly, the constant 3, 0.6 F plus 0.3 S is less than or equal to 21. Now we will add non-negativity constant since the quantity of F or S cannot be negative, so F and S should be greater than or equal to 0. Now we have formulated the mathematical model. We have to maximize, this is our objective function, this is 40F plus 30S, subjected to, these are the constant for material 1, material 2 and material 3. And now we will find, first I will just explain what I have covered in my previous lecture, that I have used the graphical method to solve this problem. This is the feasible zone by drawing the 3 constant, and these are the profit lines which we have to move from origin to upward. And here we found the profit contribution by making this point of intersection as a optimal point, and we got the solution of 25 and 20. 25 is the fuel additive and 20 is the solvent base, so our profit contribution is 1600. Now we will come to the simplex procedure. When our decision variables, the number of decision variables are 2 or more than 2, then we can't use the graphical method. Then we have to go for the another method that is called the simplex method. Now we will formulate or we will concentrate on the mathematical model. We have already explained that in the summation that Z is equal to summation of C into X. Here we have explained this expression that Z is equal to C1 X1 plus C2 X2 if there are n number of variables. And similarly these are the number of constant, and this is the non-negativity constant. Z is the objective function which need to be maximized or minimized. Cj in the objective function are called the profit or the cost coefficient. Bi, where I is 1 to m, are called the resources. This lead to the constant. Aij are the structural coefficient. Now it will be noted that the form in the previous slide is nothing but a system of m linear equation in n variables where m is less than n. A solution to this system is a particular set of n values, 0, negative, positive, which are assumed by n variables such that the system of m equations is satisfied that all the constants are true. A solution is feasible if all m variables it assumes non-negative value, that is greater than or equal to 0. A basic feasible solution here is a solution which is feasible and has at most m positive value of variables. If less than m values are positive, then the solution is called the degenerate basic feasible solution. Now when we get an equation or we transform an equation from the statement, then we have a inequality sign. The first step is how you will transform the inequality sign into the equality sign. In order to convert inequality sign constant into equality sign, we introduce the slack variable or surplus variable. An equality of less than or equal to type is transformed into an equality by addition of non-negative or slack variable. Now we will define that what is the slack variable. Slack variable can be thought of an imaginary product, each requiring for its production 1 unit of capacity from out of resources of 0 unit capacity and yielding a profit of 0. Means slack variable is does nothing, but it is simply added just to avoid the non-negativity of the solution. Slack variable corresponds to the amount of unused capacity for the constant to which it is added. Now let us take the simple expression that this was our expression for constant, and this is the sign of less than or equal to. Then by adding a suitable positive quantity S1 on left hand we have Si, so this becomes the equal sign. The new quantity is called the slack variable and it is interpreted as slack is equal to right hand side minus left hand side. Similarly, an equality sign of greater than or equal to type is transformed into an equality sign by subtraction of non-negative, which is called the surplus variable. This is the constant with greater than or equal to sign. Here we have put the minus sign and put surplus variable. Surplus variable represent an excess amount by which a particular requirement is met. Now today we will take only a maximization case. First we will define different steps which are needed in the simplex problem for in a maximization case. Step 1. First we will define the variables. This is initial step involves the identification and assigning names to each variable in the problem. Step 2. We will first state the basic problem mathematically. In this step, linear objective function and the linear constant are stated formally. Step 3. Modify the problem for simplex problem. In this, all the inequalities must be transformed into equality sign by addition of slack variable. Since we are taking the maximization problem, so we are only considering the slack variable. Now here we have the total mathematical model, that is z is equal to c1x plus c2x2, and these are the slack variable which we have added. Now these are also added in the constant s1, s2 and up to sn. These are the m number of constants. Now design the initial feasible solution. Suppose we put x1, x2 and x2, s1 is equal to 0. So we will get s1 is equal to b1, s2 is equal to b2 and sm is equal to bm. Similarly we get the s1 is equal to b1. This is the table which we have to construct or we have to make during our formulation or solving the problem with the help of simplex problem. Here this line gives the contribution or which we have taken from the objective function. This is column first, this is column 2, this is column 3, which I am going to explain in my next slide. The first row is called the objective row of the simplex table. Indicate the value of Cj, refer to the column number which are coefficient of m plus n variable. Second row provides the major column heading, and this column heading does not change. Means this basic variable, solution, coefficient matrix, identity matrix. Similarly Cb, B, x1, x2, xn, s1, s2, s3. This name does not change until we get throughout our problem solution. The first column is called the objective. This is our objective function which we have taken, that if the x1, x2 are 0, then these are the objective function. The second column points out the basic variable in the basis, and in the initial simplex method these basic variables are the slack variable, this s1, s2 and sn, and when we have put the x1, x2 and xn is equal to 0, we get this contribution b1, b2 is equal to slack variable. Third column, quantity, which I have already explained, that when x1, x2 and xn is equal to 0, then we get this column. The identity matrix in the simplex table present the coefficient of slack variables that have been added to the original inequality to make them the equation. Each simplex table contains an identity matrix under the basic variable. The matrix under non-basic variables is called the coefficient matrix. The row labeled as ZZ contains the sum of products of the number in the CB column times corresponding the coefficient under each column variable in the main body of the table. The value of ZZ for each unit of variable that is brought into the solution at the current iteration. Now the final row CZ minus JZ row called the index row or the net evaluation row. This I will also explain when I will solve the problem. Each number in the index row represents the net marginal improvement on the objective function if one unit of each variable is brought into the solution at current iteration. Now we will test the solution for the optimality. Index row of the above simplex table we will examine. If all the elements in the index row are negative, then the current solution is optimum. If there exists any positive number, the current solution can be further improved by removing one basic variable from the basic and replacing it by some non-basic. Then determine which variable should enter in the solution mix next. One way of doing this is by identifying the column which has the largest positive number. The value of CZ tells the amount by which the value of the objective function will increase for every unit of xj. Column so identified is called the pivot column or key column or the optimum column. Then we have to determine the departing, which variable should be departed. This is accomplished by dividing each number in the quantity column by the corresponding number in the key column, which we have identified by which is the maximum CZ minus JZ value. Then we identified the key element. The key element is the intersection of key column and the key row. Then we will evaluate for the new solution. If we again calculate the value of ZJ and CZ minus ZJ. If we get any positive number, then we will again calculate the value. Now the new number is found out as a number in the old row minus corresponding number in the key row into corresponding fixed ratio, where fixed ratio is the old number in the key divided by the key number. New entries in the CB column and the XP column are entered in the new table of the current solution. And again we test for optimality by computing ZJ and CJ minus Z0. If all numbers in the index row are 0 or negative, then we have reached to the optimal solution. If there is any number, then we again repeat the procedure. Now we will come to the problem. We will take the problem of two variables and we will try to solve it with the help of simplex method. There is a manufacturer who has two products P1 and P2. Both are produced in two steps by machine 1 and machine 2. The process time per 100 for products on the machines are P1 need 5 on machine M1 and M2. This is the contribution made by P1 and P2. These are the total number of hours available on machine 1, and this is the 80 hours which are available on machine. Now manufacturer can manufacture any quantity, but there is a constant of number of hours available on each machine. Now we will make the mathematical model. So our first step is the formulation of mathematical model. We will maximize, this is the 10 or 5 is the contribution from product P1 and P2. So 10x1 plus 5x2 is the objective function which is needed to be maximized. And these are the constant. This is the number of hours available on machine 1. So our first constant will be 4x1 plus 5x2 is less than or equal to 100. Similarly 5x1 plus 2x2 is less than or equal to 80 is the constant for machine. And x1 and x2 are the number of units for product 1 and product. Now the second step is to convert the equation. We will add the slack variable. Here we have added the slack variable S1 for constant for machine 1, and we added the slack variable S2 for machine 2. And similarly we add with the 0 coefficient in the objective function. This is our non-negativity constant. Now we have taken the simplified form of simplex table, and this is the objective function CZ. These are the contribution, initial contribution, these are the slack variables, and these are the total number available. So these are the coefficient of first constant, this is second constant, and we have put 1. This is our identity matrix, this is our body matrix, and this comes the final or the first simplex tableau. Here we first calculate the value of Zj. How we will calculate? Let us see. We will first multiply this 4 into 0 plus 5 into 0 and subtract it from the 10. We get this value 10. Or Zj is equal to simply addition of this multiplication 4 into 0 plus 5 into 0, that is 0. Similarly we add for each column, and when we subtract it from this contribution 10, we will get here 10. So all the values are positive, therefore this means that the optimal solution is present. So we will first take this as a maximum value, and this is our key column. Similarly, when we divide this contribution with the element in the key column, we get 100 by 4, that is 25, 80 by 5, that is 16. So out of these 25 and 16, 16 is the less value. So this is our key row, and since it is intersecting at 5, so 5 will be our key element. The slack variable S1 and S2 present the idle or unused capacity on machine M1 and M2. Since this ideal capacity will either positive or 0, the variable S1 and S2 are shown as non-negative. The basic variables are set to equal to 0, so S1 is equal to 100 and S2 is equal to 80. Now how we have calculated the value of Z, I have explained here that for gross profit, the profit per unit of S1 into number of unit of S1 plus profit per unit of S2 into number of unit, that comes the 0. Now this is calculated the final these values CZ, which I have already explained. Now we have converted by dividing new row. How you will calculate the new row? We will divide the row with the help of corresponding number or the key element. So we have divided by this 80 by 5, this is 16, and here value was 5. 5 divided by 5 is 1, 2 by 5, 0 by 5 is equal to 0, and 1 by 5. So this becomes our key row, new key row. It may be noted that x1 is now in the solution mix, and that is 16 unit of x1 are being produced. CZ value is listed as 10, the contribution per unit of x1 in the solution. This will definitely provide with a more profitable solution that 0 generated in the initial. Now we will calculate the new row. New row is equal to old row number minus corresponding number in the key row into corresponding fixed ratio. What is fixed ratio? Fixed ratio is the old row number in the key column divided by the key number. Here we have calculated the row number, new row number. So let us see that this is the row which need to be modified. This is the key row which is modified by dividing this key element. So this row we have to modify it. So this is 100 minus 80 into 4 by 5. This is the fixed ratio, and this is the old row number. So 100 minus 80 into this, that comes 36, 0, 17 by 5, 1, and minus 4 by 5. So this row has been now changed. Now again we will calculate the value of Zj by multiplying 0 into 0, 1 into 10, this comes to 10, and if we subtract 10 from 10, we get the 0. Similarly we get the plus 1, 0, and minus 2. Since plus 1 is the maximum number, so this will be the key column. And if we divide this number 36, 16 and 160, this is the contribution column, so we will get 180 by 17 and this. So 180 by 17 is less, so therefore this will be our key row and it is intersecting with the key column on this number, so this will be our key element. The new key row, by dividing the key number or key element, we get this new key row. Similarly, we have transformed the row with the help of our formula, that is, now we get this row, that is 180 by 17. Now again we calculate the row for Z and CZ minus Z. We get the value 290 divided by 17, 10, 5. And since we are not getting any positive number, this means that we have reached to the optimal solution, where x1 is equal to 200 by 17, x2 is equal to 180 by 17, and s1 is equal to 0, s2 is equal to 0, and the total profit is 2900 by 17. Now, how you will interpret this finding? Simplex tables helps to predict the effect of changes in the input factor, that is resources, and the profit margin without drawing the table fresh. Now we get the opportunity cost. The term ZZ, what we get, that is 2900 divided by 17, indicate the opportunity cost. If we do not utilize a 1 unit of x1, there is a loss of profit 10, and non-utilization of 1 unit of x2 cost rupees 5. If you see the final table, this is 10, this is 5. If we do not use 1 unit of x1, we will have a loss of 10. If we do not use the 1 unit of x2, we have a loss of 5. Now what is the shadow cost? Shadow cost, if you see the final equation, that 2900 by 17 is equal to 10x1 plus 5x2 plus 5 oblique 17s1 plus 30 plus 17s2. Now the coefficient of s1 and s2 are called the shadow cost. They represent the decrease in the optimal value of the objective function resulting from a unit increase in a non-basic function. Now we will calculate the value of s1, that is 100 minus, if we see the first equation, we will simply put all the things into right hand side and we get the value of x1 from the first constant, that is 100 minus s1 minus 5x2 divided by 4. Similarly, we get the value of this is also x1, so if we equate both, we will get the value of x2, and x1 we will get, if we put this value into the objective function, we get 2900 upon 17 minus 45 s1 divided by 17 minus 30 s2 divided by 17. So here, if this is the shadow cost, that if there is any unused quantity of s1 or s2, this will reduce, or if there is any this slack variable, then this will reduce the profit margin by this much amount. Similarly, unused or slack variable for machine 2 will reduce this much quantity of the from the objective function. Now these are the different software which are available on the site, from where you can either solve this linear programming method with, by simplex problem with the help of either you go manually, or you can take the help of different software which are available, freely available on the internet. That is, first is Lindo, and the site is Lindo, www.lindo.com, and similarly lingo.com. Or you can also solve this simplex method with the help of Excel, MS Excel, through there is a one icon that is called the solver, and by going to the solver you can solve this simplex method with the help of this solver. There is another software available that is called the manager, where you have to put only your values and you will get the optimal value of your decision variable by within few seconds. And there are other applications oriented softwares are also available in the market, which can be applied as per the requirement. Now we will come to the conclusion that what you have learned from the today's session, that linear programming problem has a wide applications in the various problems of engineering, business and industries. Linear programming must have well-defined objective function. Unless and until you have a well-defined objective function, you cannot solve this linear programming. You have an objective function which either needs to be maximized or which needs to be minimized. In this session, we have taken the maximization problem. In the next session, we will go for the minimization problem. The decision variable interact with each other. Suppose there are two decision variables, so they interact through some constant. In our example, we have the machine hours. In second example, machine hour is a constant. So these two decision variables, the number of products produced for P1 or number of units produced for P2, they interact with each other with this constant. Means suppose we have to produce the product 1, then this will limit the production of P2 on machine 1. The objective function and the constant are the linear function of the decision variable. This is the most important portion of a linear programming, that objective function, constant, all should be the linear function of the decision variable. We cannot solve a non-linear function with the help of simplex. There are available some technique for non-linear functions that we will come later on. The linear programming with two variables we have solved with the help of graphical. If we have more than two, we have to solve it with the help of simplex method. A non-degenerative, non-negative solution which satisfied all the constant, as you have observed that in the final table we get a solution where we get all the negative numbers, or there is no positive number, which indicate that it does not exist any further, we cannot improve further. So our profit or the cost, whatever be, if we want to maximize the profit, then this is the optimal solution where we get the final solution. This is my contact information, and this is my email ashish_ka@yahoo.com. and if you have any difficulty or any problem in this regard, in either simplex problem or the graphical problem or any type of problem related to the system method block, you can easily contact or you can just mail your queries at this ashish_ka@yahoo.com. Thank you.